I'm Jack Sifri. I work in Agilent ESOF. And as you see, the title of the paper is How to Make Your Existing Designs More Robust, or Creating Robust Designs too. This is a wide topic. It has a lot of things that I can share with you. But in 20 minutes, I hope I can give you an overview of the methodology and how it is used. So what is robust designs? What I mean by robust design is design that will work no matter what. If I change the voltage supply by slightly, it still meets specs. If temperature variations, temperature goes up or down, it's not sensitive. If the process, when you fabricate changes, it still meets the spec. It is not sensitive to that process variation. So it's really a very low variability, consistent, high-performance design methodology. And I always like to start my talk by showing, like they say, a picture tells 1,000 words. I always like to show an example to kind of give you an idea what I'm talking about. This is a wafer, and it has two amplifiers. The two amplifiers are the same specs, same everything. The only thing is one amplifier was designed using the standard design techniques. The other one using that robust design techniques that I'm going to talk about. And we put them on the same wafer. So to eliminate saying, different process, different wafers, we put them on the same wafer. And the results came. This one is the gain versus frequency. You can see the variation on the traditional design. And you can see the wafer probed results, how tight it is with the robust design technique. So this is kind of an illustration of what I will be talking about. When we fabricated this in the foundry mentioned to us when they fabricate this that the process shifted a little bit to the left, lower frequency. Notice the standard design shifted a lot to the left. Notice this design, the robust design, shifted to the left because the process, but a little bit, because it is not as sensitive. We liked the results here, and we said, hey, let's do another experiment. And the other experiment we did is we added a mixer and an LO amp to that amplifier. We constructed this macro cell, and we put it in the same wafer, and we fabricated this whole macro cell, in the same process, same wafer. We did this. And this is the results. This is the wafer probed results. Notice the conversion gain at 20 gigahertz. How the variability is very wide here. And notice how tight it is with the robust design techniques, what we call the design of experiment design technique. So you can see it is really valuable to learn this design methodology and be able to apply it to your designs, because it will help you get high yield and get your designs to work no matter what from the first time. So let's understand the results. That amplifier I showed you first, if I plot the gain on the x-axis and how many met the specs, notice that the first one, the standard design techniques, has a big, wide variation. The gain ranges from 10.5 or 10 to 14 dB gain. Whereas this one, the robust design technique, is very tight. All of them is around 14 dB gain. So this takes me to discuss with you the process of robust design. How do we deal with it? You have a design. You run that analysis, design of experiment analysis, and you find out you are on curve 1, or maybe curve 2 or 3. But wherever you are, there is always a room to improve your design. You apply these tools, the design of experiment and the yield sensitivity histogram tools, to move you from one curve to another curve. You keep doing this until you get to curve number 4, which is very low variability and consistency, very tight. And then at the end, you center your design to the spec. If you need 13 dB gain, you move this curve to the 13 dB gain. This is basically the process of creating robust design. That's the process I use when I design. The two tools to apply to detect where the problem is design of experiment and yield sensitivity histogram. And I would like briefly to discuss with you what is design of experiment for those who maybe haven't used it. This example I'm showing you here is a system level example, but you can use it on an IC, you can use it on a board design, you can use it on SMT components, it's very versatile. Just I want to start with a system level example, and then I'll take you to an IC example. What I have here is 4 amplifiers and a filter in the middle, okay? And what you see here in between these modules is an inductance of a gold ribbon. So if you have a system tray and you put a gold ribbon between the modules, there's an inductance associated with that gold ribbon. And I go ahead and simulate this system with the gold ribbon, 0.15 nanohenry nominal value here. I go ahead and simulate this, and I get about 55.2 dB of gain for the whole chain here. That's the nominal simulation. But now what I want to do, I want to see how robust is my design, how sensitive it is. So I'm going to run design of experiment on it, and what I do is I build this experiments. What you see here is a table that has the 4 inductors between the modules, L1, L2, L3, L4. Those are my variables, okay? The inductance between the modules. If I have 0, this means my inductors, all of them, the inductances are nominal value, 0.15 nanohenry. And I do get my 55.2 dB gain. But now I have a variation here. When I have -1, that means the inductor is 5% less. And if I have +1, that means the inductor is plus 5% higher. 5%, just like higher inductance, a bit higher or lower. So notice I have all the combinations. Because I have 4 variables, I have 16 experiments of minuses and pluses, just varying that inductor plus or minus 5% from nominal. And I measure the gain. Every time I change the inductance, I simulate, get a different gain because the inductance. From this data here, what I do next is I take for L4, for the bond ribbon L4, I take all the -1 when the ribbon is short by 5%, and all the +1, and I take the average gain of the -1 and the +1. And what is the difference? We have 55.39 dB gain and 55.04. The difference is 0.35 dB gain. This is for L4. It's a little bit change. It's not that bad, 0.35 dB gain change. Next, I take L3, the third inductor, and I do the same thing. I take all the -1s, calculate the average gain, all the +1, calculate the average gain, and the difference in the gain, 6.8 dB. Not 0.35, it's 6.8 dB now. Automatically, you know L3 is critical. The system is very sensitive to L3 because look at the change. So if I plot so far, if I plot what I call the effects of L4 and L3, notice L4 is horizontal, no change in gain, it's 0.35 dB. But L3, the gain changes from 58 to 51, so a big change here between -1 and +1. Okay? Give you an idea what DOE really is telling you where the sensitivity is. And then we can do the same thing, not only the inductance separately, you can do the interactions. Like here I have the interaction between two inductors, L1 and L3. And I do the same thing. I take the +1s and I calculate the average gain and the -1, and I calculate the average gain, and I see the coupling between the inductances, the effect of the coupling is very minimum, 0.05 dB. The bottom line with DOE is you can do all kinds of interactions and effects, and you can build an equation when you do all this analysis. So the gain is 55.2, and all these effects from the inductances. This is very difficult to look at, an equation, but you can always plot it in a Pareto chart. And the Pareto chart automatically tells you L3 is your dominant effect, is your problem. This is what you want to fix in your design if you want to make it robust. And I went ahead and I took this design and I put it in ADS, because ADS has that tool, the design of experiment. You don't have to do it manually. You can just click simulate, and the same thing happened. You can see the L3 effect of the inductor is the dominant one, and these are the effects plots, and this is L2, and other things, the coupling and everything. But the bottom line is, this is what you should concentrate on fixing the design. So in my past job, long time ago, I did work on something similar. I was working on a space application, a tray with modules. Everybody designed their module, whether it's a mixer or an amp or an LNA or a PA, and everybody tested their PA and their modules. It worked fine, gain and power. When you put the whole system together, it was short. It was short with the gain and power output. It didn't meet the specs. And we had a deadline. We really have to deliver, and we don't have time to go back and redesign, and we couldn't find the problem. So I was working in this area before. I ran a DOE experiment, design of experiment, on the impedances, input and output impedances of each module, 20 variables, and found out that this is the sensitive area. Just like the example I showed you, kind of. This is the sensitive area, and we don't have time to go and redesign the modules. So the action that was taken is combine these two modules together into one module to eliminate that bond wire or ribbon and the variation. And it solved the problem. We got the power output, we got the gain, shipped the product. So it's very useful to do this. Now, what I showed you is at the system level, design of experiments. This example here, I want to show you how you can apply it to your IC design. It's a circuit level example. In this example, I have a two-stage power amplifiers. That's stage 1, stage 2, output power, it's an IC. This is the schematic, input matching network, FET1, interstage, FET2, output matching network. And I simulated P in, P out, and it looks really nice. It's very linear here, compressed very smoothly, and I meet my spec over 26 dBm output power. So nominal simulation looks really good. But then I ran Monte Carlo analysis, vary all the components by plus or minus 5%, and I want to see the results. And guess what? This is what I got. This is the Monte Carlo simulation, and you can see how wide the variation and how many failures I have here. Now, what do I do? The design has a lot of components, matching networks, and where do I go? What is causing this problem? So in ADS, I took my power amplifier and I ran design of experiment on it with, I have different DOE, design of experiments, but this is one of them, on 6 capacitors. 2 capacitors in the input matching network, 2 capacitors in the interstage matching network, and 2 capacitors in the output matching network. I went ahead and changed those capacitors plus or minus 5%, and I click simulate on design of experiment. This is the results I got. What is DOE telling me is 100% of my problem in the yield is coming from capacitor C2 in the interstage matching network. So now I know exactly what's causing the problem, C2 in the interstage matching network. And it's telling me that the power output is ranging from 27 to 12 dBm, just like the yield Monte Carlo told me. And this is the capacitor C2, and it's right here in the schematic. You know, it's like an X-ray machine. It really tells me, pinpoint, this is the problem, what's causing the problem. So I ran yield sensitivity histogram on the design. And again, I don't have too much time here to explain this, but basically, you can see on the interstage matching network C2, running the yield sensitivity histogram tells me if C2 is lower, I get 100% yield. And if C2 goes plus 5%, a little bit higher, the yield goes to 0. That's what's causing the problem for me. So even that yield sensitivity histogram is telling me this. So what I did, I took C2, I lowered the value, re-optimized my circuit, and I ran Monte Carlo yield analysis, and you can see the difference now. It solved the problem. I detected where the problem is. We wrote an article with Skyworks. This is an article in Microwave Journal, Innovative Integrated Approach to 3-5 Circuit Design. Skyworks worked on design of experiments on a dual band power amplifier, and they used design of experiments, and they were able to ship millions of chips every month after fixing their design using design of experiments. You can read this, it's in the CD. But basically, they started with 5.5 dB variation, and the current is 50 milliamp variation, and they ran DOE twice, and they dropped it down to 15 milliamp variation and 2.5 dB variation. That was the paper that was written in Microwave Journal. You can read it. And they were able to kind of ship a lot of high yield, a lot of chips. So in conclusion, basically, I mainly described to you the design of experiment, but we also have the yield sensitivity histograms. Those tools together could really take any design, whether it's board or IC or system. And I have a lot of examples. I could really talk about this for a whole day. I have a lot of material, but in 20 minutes, I hope I gave you a brief introduction to this topic. If you need more information, please stop by the booth. I have it on my computer, a lot of examples, and I can give you a lot more information on this. Thank you very much.